Professor John Geake, Professor of Education at the Westminster Institute of Education, Oxford Brookes University, United Kingdom, as a keynote presenter at the Australian Government Summer School for Teachers of Mathematics at the University of New England in January 2008. John's presentation, entitled How the Brain Does and Does Not Do Mathematics, was presented here, and he's going to give us an overview of that program. John, I wonder if you can just tell us what the main focus of your presentation was.
Certainly, Russell. Well, the main focus was this: contemporary research in cognitive neuroscience, which essentially means brain imaging in the main, has some relevance to educational practice, providing, and it's quite a big if, we take due note of the limitations of this research. And I pointed to a number of these, not the least of which limitations on the types of questions we can ask within contemporary cognitive neuroscience when you've got someone shoved up the bore of a large fMRI imaging machine. There's many things that they are simply not able to do or respond to, and that limits how informative it is for education in a classroom. There's also limitations to do with how we analyse the data, how we select subjects, and so on. Nevertheless, there's, 500,000, maybe 1 million studies on brain function over the last 15 years. Some clear trends have emerged, and the clearest and the one that holds the most implications, I think, for education is that how the brain enables us to do high-level cognitive tasks like mathematics is by involving a myriad of functional modules distributed throughout the brain and interconnecting them in a synchronous and functionally relevant way.
Thanks, John. I was just wondering if you could tell us how this presentation was relevant to contemporary mathematics teaching.
Well, I think at a meta level, it's suggesting that teachers as professionals should be encouraged to enhance that professionality by taking on board some of the information and the results that are coming from this line of research and filtering it through their own needs and objectives to better understand how kids are learning and perhaps how to enhance the pedagogy, curriculum design and so on. That, as I see it, is the task for the teacher professionals. My task is to provide the research evidence in a form that's understandable. One interesting phenomena in recent education has been the rise of so-called brain-based ideas in education. And we hear about so-called left and right brain thinking and sensory learning styles, visual, auditory, kinesthetic and brain gym and so on. But distressingly, what we learn from neuroscience is that these are not brain-based at all. They don't have a basis in how the brain actually works. And I'll perhaps talk more about that later in the interview. But I think it's important for teachers to see, and I think by understanding more about how brains do work, they'll come to see that these are so much snake oil.
Right. Great. I'm just wondering if you can tell us some of the key ideas or messages that you would hope that the participants of the summer school may take back to their school environment.
Okay, well I guess the main two messages, the first one on how the brain does do mathematics, and that's to do with exploiting this interconnectivity. And interestingly, you get different circuitry involved with each different type of mathematical operation. And so there are, if you will, the potential, I think, as we understand this circuitry better, for designing remedial interventions, say, that might be more effective for those kids who don't get on top of mathematics learning, where we know that simply giving them more examples of what they can't do isn't particularly effective and quite demoralising. Secondly, some of the areas implicated in nearly all of the circuits involved in doing mathematics, the parietal areas, so these areas at the top of the back of the brain, that seem very important for representing magnitude, for representing spatial thinking and concepts and so on, might suggest to us that there are approaches to teaching which can exploit that. And one example I suggested was Logo Turtle, where the children move around their classroom space to decide what symbolic steps they need to program into the computer. So they're moving from a propriocentric to a symbolic range, so they're getting into the maths through doing things that their brains evolved to do. My point in opening, of course, that our brains didn't evolve to do mathematics. They evolved to help us as primates to find our way home and find food and live in trees and so forth.